Last time we discussed fundamental theorem of calculus part 1. Part 1 draws connections between the antiderivative of the function and the indefinite integral of the function, saying that they are actually the same thing. Part 2 of the fundamental theorem of calculus will allow us to actually calculate a definite integral, so the area under the curve, with the information about the antiderivative. Let's read through the statement and then draw a picture that corresponds to it. So what we have here is that f of x is a continuous function on some interval from a to b. So let's actually sketch it as we go along. I have some continuous function f of x. I also have some interval a to b. And the other piece of information I am assuming I have is the fact that capital F is any antiderivative of my original function. Then, for x between these two values that I'm allowed to work in between, what this is saying is the definite integral, which is the area between the curve of the graph of the function and the x-axis. So area between f of x and x-axis is equal to the value of the antiderivative at the right endpoint of the interval minus the value of the antiderivative at the left endpoint of the interval. Let's see if we can somehow justify this using the graph. So what I have here is left endpoint A and right endpoint x. This is the area between the function and the x-axis between a and x by the definition of the definite integral. If I have the value for the antiderivative, any antiderivative, recall that they only differ by a constant, what this is saying is that I can calculate the area by calculating the area at x minus calculating the area value at a. So really, on the picture, what this corresponds to is if I take the area from 0 to x, and then I subtract the area from 0 to a. What I end up with, of course, is exactly the area in the middle. Now, this is a quite hand-wavy description of the proof of the result. There is an algebraic way to approach the rigorous proof of why this is true, but I'm not going to go through that. It doesn't really provide additional insight, and we will only utilize the actual theorem for calculation purposes, which we're going to do shortly, and we'll see how this works. The one other piece of information that is useful to have is actually a notation, a shorthand that we're going to use for it. It's useful to introduce not quite the full step, but kind of like a middle step here, which we will see will become really quite handy in calculations. So the notation is going to be that if I want to calculate f of x between a and b, I will introduce the notation of a vertical bar, a at the bottom, b on top, and this notation will mean that I first plug in the top value minus I plug in the bottom value. So first b goes in minus a goes in. This is supposed to replicate what happens on the integral, except for with the antiderivative, we've already performed the integration, and this is going to be one step before the actual substitution of the values. Let's see how we can utilize this to actually calculate some areas. Find the area under y equals f of x squared between 0 and 4. I do find it quite useful to still sketch graphs to make sure that the areas you're computing are the areas you think you're computing. This is an easy graph, so you can picture this in your head, but it's generally a good idea to sketch out the graph just to make sure everything is the way that we think it's going to work out. So this is the graph of y equals x squared, and I'm interested in the area under it between 0 and 4. So 0 to 4. I am interested in this area right here. By the definition of the definite integral, this is exactly the integral between 0 and 4 of x squared dx. Now, the first step that I need to do, according to the fundamental theorem of calculus part 2, is figure out what is the antiderivative of this, any antiderivative of this. Now, this one is an easy one. It's x squared. So this is just a power rule. I'm going to add 1 to the power and divide by that number. So x cubed over 3. Now recall that it can be any antiderivative. So I'm going to assume that it's the most convenient antiderivative, the one that has c equal to 0. Now, what the second part of the fundamental theorem of calculus part 2 says is that I have to compute that between 0 and 4. And this is where our vertical bar notation is going to come in particularly handy. So what the vertical bar says now is I have to plug in the top number minus I have to plug in the bottom number. So what do we have? 4 cubed over 3 minus 0 cubed over 3. So altogether we'll get 4 cubed over 3 or 64 over 3. That's it. That's the entire area right here. Isn't this way better than the Riemann summations? Remember how much time we spent computing the areas of the little rectangles and summing them all up in questions like the leaf or anything else like this, or when we broke up this interval into pieces and went through the calculations with a finite number of rectangles? This is the way that we're going to calculate areas from now on. Not only is this way faster, it's also exact. So this is not an approximation, this is the exact area that we are after. The reason that the plus c here is not necessary is basically because it will get subtracted in the process. So this could have had a plus c, and this term could have also had a plus c. So you can think of c's as being canceled out because you're going to do this twice. Let's see how much faster the area of the leaf calculations are going to be using our newly developed understanding of how the integrals work. So here, I would like to compute this area, which means that I am after the definite integral between the two intersection points, which you can calculate to be 0 and 1. So between 0 and 1 of my actual function. Now, if I'm after the actual leaf area, so the entire leaf, then of course I notice that I have to double this integral to take care of the bottom half of the leaf as well as the top. What are we going to have here? So as discussed previously, I cannot split integrals across a product. I'm going to have to factor things out and then apply other rules. So what I'm going to have is the integral between 0 and 1 of x minus x squared dx. What is that going to end up? What am I going to end up with here? So what do I have in terms of the antiderivatives? Notice that what I'm mostly interested in as the first step is the antiderivative, and then I'm going to, once I have computed the antiderivative, plug in the points. So the antiderivative of this thing is the antiderivative of x, which is x squared over 2, minus, as per minus here, the antiderivative of x squared. So that is x cubed over 3. And now all I have left to do is compute this between 0 and 1. So again, as per the fundamental theorem of calculus, I plug in the top number. Now here I'm going to have to plug it into 2 spots, minus I plug in the bottom number. Notice that at this point I actually have a little bit of freedom. I could factor 2 in and then plug in 0 and 1, or I could do it at this point. It really doesn't matter. So what I'm going to have is 2 times 1 squared over 2 minus 1 cubed over 3 minus 2 times and then plugged in 0. So 2 times 0 squared over 2 minus 0 cubed over 3. Altogether, I'm going to end up with 2 times 1 over 6 or 1/3. Exactly the same number as we ended up with when doing this using Riemann sums. Now, once you do this a few times, this method will be even more efficient, but even now, it took me just a couple of lines to figure this out, whereas the entire Riemann sum calculations took a couple of slides to really set up and make sure that it works, not to mention that it required proficiency with operating and massaging sums, as well as calculating limits. This method is way faster, but it had to be built up on the Riemann sums and the understanding of how the areas work. Let's take a look at a few other examples just to see if there's any kinds of other things that we can notice about them. We're here asked to sketch and find this integral. And again, if you didn't, for example, have to sketch it, you wouldn't have to necessarily. If you weren't asked to sketch it, you wouldn't have to sketch it necessarily. But I strongly recommend that if this is something that you can sketch, that you do sketch it. So what does y equal 1 minus x squared look like? Well, 1 minus x squared is just a parabola looking down. So what I'm going to have is a parabola looking down and is shifted 1 unit up. So something that looks like this. One thing that's easy to sort of fall into trap of is to think that parabolic shapes are basically circular shapes. That's not true. So this is not half a circle, much like a sine or cosine curve that create also these types of shapes. These are not half circles, so watch out for that. That would not be a shortcut for actually computing the area. So this is now the function that I'm interested in between -1 and 1. Now the definite integral tells me that what I'm after is the area here between -1 and 1. I can compute it as is, or I can also notice a symmetry. I can see that this half is going to be the same as this half. So instead of computing this integral, I can compute twice the integral from 0 to 1 of 1 minus x squared. Notice that what happens at the last step is that you plug both of those points in to the antiderivative. Plugging in 0 is always easier. So if you can reduce something to be at 0, it's always probably a little of a time saver. So what I have now is 2. I have to find the antiderivative of the inside, 1 minus x squared. The antiderivative of 1 is just x. The antiderivative of x squared is x cubed over 3. And I have to calculate this between 0 and 1. So again, first find the antiderivative, then plug in the numbers. We plug in the top number minus, we plug in the bottom number. So here I have 1 minus 1 cubed over 3 minus 0 minus 0 cubed over 3. So altogether, I will end up with 4/3. Again, notice that plugging in 0 is actually quite a bit easier here, because I noticed that plugging in 0, this whole thing becomes 0, and therefore I only have to actually calculate the one term. Even if you have a calculator, plugging in numbers is going to be a lot faster if one of them is 0. What about this next one? 1 over x dx. If we compute this as is, let's say you were really lazy, were not following instructions and didn't want to sketch it, what would we do in terms of calculations of this integral? What is the one or any antiderivative of 1 over x? That's the one antiderivative that doesn't quite follow the power rule. The antiderivative of that is ln x. And in fact, it's actually ln of absolute value of x. Now, most of the time we will be dealing with positive numbers, so we can drop that. But remember that ln cannot take in any negative input. So normally there's that restriction on that. And it has to be now evaluated between 0 and 1. We plug in the top number first, ln of 1, minus ln of 0. Try plugging this into your calculator and see what it says. It will give you an error, and that is because ln of 0 does not exist. So what does that actually mean? Why can't we evaluate this? I thought that we had developed a pretty straightforward process that works every time. Well, the one thing that will help is to interpret this in terms of an area and see, is there anything wrong with the graph that happens at that point? So the integral states that I have to look for the area between 0 and 1, between the graph of 1 over x and the x-axis. So I'm going to have to draw the graph of 1 over x. The graph of 1 over x, the reciprocal function, has two branches like these, and the area I'm interested in is between 0, which is right here, and 1, let's say somewhere here. Well, we notice the problem right away, because, of course, this area goes on forever in the vertical direction. The vertical y-axis here is actually an asymptote to our graph. So while it approaches it, and approaches it infinitely closely, it does go on forever in that direction. This is, of course, a problem. This function is not continuous on this interval. Recall that continuity was one of the assumptions of the fundamental theorem of calculus. If the function we have is not continuous on the interval given, then we cannot apply the fundamental theorem of calculus because it simply will not produce a valid result. These types of integrals is something we will talk about next time when we talk about improper integrals. What we're going to focus on for the rest of this lecture is not computations with necessarily one function, but rather extending it to compute areas between two functions. So notice the different setup of a problem. I have two different functions, and I would like to compute the area enclosed between them on some interval. The fundamental theorem of calculus and the definition of the definite integral allow me to compute the area between one function and the x-axis. What about the area in between the two functions? Now, luckily, there's something I can do here. If I can compute the area between the function and the x-axis for f of x, and if I can compute the area between the function g of x and the x-axis, then the difference between the two is going to specifically give me the area bounded by them. So the shaded area here is going to be the area, and therefore the definite integral between a and b of the function f of x minus the area bounded by the function g of x and the x-axis. Okay, so once again, back to the sketch. If I take the definite integral of the function f of x, I will be computing this entire area. If I take the definite integral of the function g of x, I will be computing this area. And this area is exactly what I don't want, so I will be subtracting it out. Now, altogether, remember that if the integrals have the same, what we call limits of integration, I can put them together. So this can give me one definite integral between a and b of the function f of x minus g of x with respect to x. We can sort of generalize this idea because what I will be doing every time is looking for which function gives me the top area, the larger area, and which function gives me the lower area, the one that I will be subtracting out. So in sort of layman's terms, I can also call this my top function and call this my bottom function to see that overall I actually have, in order to compute the area between two functions, I can take the definite integral on the interval where I'm interested in, top function minus the bottom function. Now, this means that more than ever, it's important to actually produce a sketch because I need to know which function is on top, which one has a higher values of y, and which one is on the bottom, which one is the one that will produce the area that needs to be subtracted out. A sketch in these problems will be instrumental, and let's see why that is the case and how it would work. For the first example here, we would like the area enclosed between x squared and root of x. So we'll start off by producing, you guessed it, a sketch. So what I have is my sketch here. I'm going to make the most general type available. Y equals x squared. So this is my x squared parabola. And my second graph, y equals root of x. Now root of x is actually only defined for positive values of x. So this is going to be a sideways parabola, but it's only going to be for values of x that are bigger than 0. So I can immediately see why I can calculate the area enclosed. This other graph doesn't continue off, let's say, in this manner, therefore producing some unbounded area. I can see that the only enclosed area of this sort of leaf shape, this is the area I am going to be after. Now here are two pieces of information I'm going to need. First of all, I'm going to need to know which function is the top, which one is the bottom, and here it's fairly clear that the top function is square root of x, and the bottom function is x squared. This would not have been immediately obvious just from their formulas themselves, but the other piece of information that I need are where are the points that I'm computing in between. I need to know what is the coordinate of each of the points of intersection. Now, because these are simple graphs, I can sort of see that this is 0 and this is likely 1. But let's go through the full procedure in order to figure out what are the points of intersection, because for more complicated graphs, this is going to be a necessary algebraic algorithm. Points of intersection can be determined by simply setting the two functions to be equal to each other. And so I have this equation. There's a number of ways to actually solve it. Go through whatever is more comfortable and convenient for you, but you should end up with having two roots, 0 and 1. So now I know what are my points, the endpoints of the interval, and also what are my functions. Again, let me write this down in terms of the very informal top minus bottom. The top in this case is square root of x. The bottom in this case is x squared. Now, the other thing that I would like to actually point out is, let's think about once again why this works from the graph. If I take the integral of root of x alone, that what I'm between 0 and 1, then what I'm computing is the area under this curve, between this curve and the x-axis. So I'm computing this entire area. If I then take the integral of x squared, then what I'm computing is the area between 0 and 1 under this curve. If I'm subtracting the two, then I'm exactly subtracting this area away from the bigger one, leaving my leaf shape, which is the area that I want, untouched. Now, it's all about actually computing the antiderivatives and plugging in the numbers. So first of all, the antiderivative of square root of x. Well, it will be easier to see what it is if I rewrite this as x to power 1/2, and then I can simply apply the power rule. X to power 1/2, I'm going to add 1 to the power, so 3/2, and divide by that power. Minus x squared. What is the antiderivative of that? That's simply x cubed over 3. And now I have to compute all of this between 0 and 1. Now I'm going to plug 1 in for both of those things, minus I plug in 0 in for both of those things. What I will actually end up with is 1 over 3/2 minus 1, minus, when I plug in 0, both of these guys are actually going to be 0, so they're not going to give me anything else interesting. If I put these two terms together, I will get 1/3. Therefore, the area of this region is equal to 1/3. Great. Let's do another example. What about the area enclosed between y equals x and y equals x cubed? So here, once again, as I recommended, start with a sketch. Otherwise, you won't know which one's the top, which one's the bottom, or how to really perform the calculations. Y equals x is a diagonal line. Let's pretend this is straight. I can do better. There we go. This is my y equals x. What about y equals x cubed? Y equals x cubed is a snaky shape, and you got to be careful about drawing it in. Remember your power domination laws is that the smaller power will dominate near the origin, which means that x cubed will be flatter than x near the origin. So it's going to be something that looks like this, and then eventually, because the power domination will take over for large values of x, it actually has to surpass it and increase faster and faster. This is now the graph of my y equals x cubed. Now, what I notice immediately from the graph is that I actually seem to have 3 points of intersection. Again, these graphs are simple to draw and therefore simple to spot points of intersection on, but in general, this is something we really got to be careful about solving. So let me go through the points of intersection here. In order to find points of intersection, I'm going to set the two functions to be equal, and here is the reason I'm going to go through this one careful, is to remind everybody that you do not divide, you factor. If you divide, you're going to lose roots. If you factor, you're going to see all of them. So instead of dividing, I'm going to move everything to one side and then see if the two terms have anything in common. Well, I can see that they have x in common, so I can factor that out and end up with this equation. The product of things is only equal to 0 if one of them is 0. So either x is 0 or x squared minus 1 is 0, which means that x squared is equal to 1, which gives me x is equal to plus and minus 1. This gives me 3 points of intersection, 0, as I can see on the graph, -1, as I can see here, and 1, as I can see over there. This is another reason why the graph is such an important tool, because what some students will inevitably forget to do is include the -1 as a solution here. So you will jump from x squared equals 1 to x equals 1 and forget that -1 ever existed. The graph kind of reminds you of the fact that there has to be another point of intersection here because the cubic has a snaky shape and therefore will intersect the line once again. The graph provides a really good checkpoint for the algebraic manipulations. So points of intersection calculations aside, let's now talk about how to calculate the area actually enclosed between the two graphs, which will consist of these two pieces. So notice that I cannot simply set up the integral between -1 and 1. And that is because the top function between -1 and 0 is not the same as the top function between 0 and 1. On the left side here, the top function is the cubic. On the right side here, the top function is the linear one. The top and bottom functions are not consistent throughout the entire region, so one interval will not do. So what I can do is set up two separate intervals. I can set up an integrals. I can set up an integral to compute this first area, taking the top function to be cubic and the bottom to be y equals x, and then the second integral for this area. What I will, though, realize if I do this, and if I stare at the graph for just 1 second longer, is that this area will be negative, while this area will be positive. And because both of the graphs are nice, odd functions, they're symmetric with respect to the origin, these two areas will be the same. So if I set up the integrals that way, I will actually end up with area being equal to 0. While the integral computes signed area and therefore is negative and positive, what the question is asking is for the actual area enclosed between these two curves. So I need to modify my setup to allow for that. I can either still set up two integrals and then take the left one with the negative sign in the front to compensate for the negativity of the integral itself, or I can also realize that all I have to do is set up the integral for one of these regions and then double that, because the other half will look exactly the same. So let's do just that. The total area enclosed is then twice the area between 0 and 1, twice this area here. And the area here is going to be the top function here, which is y equals x, minus the bottom function here, which is y equals x cubed. The next step is to compute the antiderivative. The antiderivative of x is x squared over 2. The antiderivative of x cubed is x to the 4th over 4. And now I have to evaluate them between 0 and 1. You plug in 1, you plug in 0, you figure out what your number is. I will leave the algebra to you. This is another example of why the graphs are so important. This graph is the only reason that we would recognize that the areas being negative and positive actually matter. Let's take a look at yet another example of areas and see how we can set something slightly more complicated up. What we are asked to do here is determine the area of the region bounded by y equals x squared, so the standard parabola, by the line x plus 2 between the two endpoints. So sometimes, like in the questions before, we're just asked for the area enclosed between the two curves, which means that we have to ourselves go through the calculations of the points of intersection. Sometimes, some of the points are given to us. Like here, we're specifically told that we're interested in the area between -2 and 3. Whether or not they happen to be intersection points is yet to be determined. So let's draw these graphs. Y equals x squared, I'm actually given a grid, so I'm going to plot points somewhat carefully on it. Y equals x squared goes through 1, 1, 2, 4, 3, 9. So there's going to be the beginnings of my parabola. And I'm going to try to somewhat reasonably sketch the curve of the quadratic function, okay? Let's assume that this is not drawn by hand, but rather it is drawn by hand, so pardon my not terribly smooth transitions. There we go, this is not bad at all. The second graph that I'm interested in is y equals x plus 2. So that is the line of slope 1 of y-intercept 2. So y-intercept 2 is here, and the slope is 1, which means my line is going to go through the grid points exactly. There we go. Great. Now, the other piece of information I have is that I want to compute the area between -2 and 3. So it's kind of like cutting your window short. All I'm interested in is the area between here and 3. So over here. So what are the areas enclosed between the two graphs on this region? Well, I noticed that it's this area here, and then this area actually enclosed between the curves here, and then this other portion here that is being cut off by my x equals 3 line. So what it looks like is 3 different pieces. Therefore, I'm going to have to set up 3 different integrals. Now, I also noticed that that makes sense because here the top function is my purple parabola, whereas here the top function is my blue line. So the top functions are different. The integrals are going to be actually quite different. Now, whereas I can clearly see what top and bottom functions are on each interval, what I don't yet know are what are all of the endpoints of each interval. I know that this is going to go from -2 to whatever this point is, but I don't know what the coordinates are. And then the next integral is going to go from this point that I don't yet know to this other point that I also don't quite yet know. These 2 points are the points of intersection between my line and my parabola, so that's my first order of business. Points of intersection. Now, again, if you draw the graph somewhat carefully, you will probably, because this is just a parabola and a line, you will probably notice that these particular points fall quite nicely right on the integers -1 and 2, but you do have to support with calculations algebraically, just because your graph might have been just very lucky or very inaccurate. So we're going to solve this quadratic equation. I'm going to leave this to you, whether you prefer to use quadratic formula or you prefer to factor it out. My only point is that you have to solve this algebraically. You cannot just eyeball from the graph. The graph provides a visual support for it, but it's not the proof of the finding of the points of intersection. So here I will though have x is -1 and 2. So altogether, the area enclosed between these curves is first of all going to be the area enclosed here, which is the integral between -1 and -2 and -1 of my top curve on this region, which is the parabola, minus the bottom curve on this region, which is a line. So x squared minus x plus 2. Be careful about your brackets here. Don't forget that this minus will have to affect everything in this bracket, so don't just omit the brackets altogether. This integral will calculate this first area here. Then I need to calculate this piece. This will be the integral between -1 and 2. Those are my 2 points. The top graph here is going to be x plus 2. The bottom graph here is going to be x squared. So in this case, I have x plus 2 minus x squared dx. And then finally, for my third piece here, I'm going to have to go between 2 on the x-axis and 3 on the x-axis, which was my sort of insisted cutoff, not a natural point of intersection. And then I'm going to have, once again, that the parabola is the top graph. So x squared minus the line is the bottom graph, dx. Notice that while these 2 integrals have the exact same inside, they cannot be combined because their limits of integration are not next to each other. If this integral started with -1 here, or if they were somehow the same, that would be one thing. But as written, they cannot be combined just because their insides are actually the same function. From now on, For the rest of the calculations, this is going to be fairly straightforward. You simply have to determine the antiderivative of that and then plug in the top and the bottom points. So I'm going to leave the rest of the calculations to you. The setup here is the most essential part. Now, this example serves as a further support for the fact that graphs, especially because you guys are in front of computers and can always ask Desmos to graph things for you, are a key step in determining what the area that you want to calculate is and how to put these integrals together.